Hello and welcome to the video lecture on chemistry of carbohydrates. This is based on the study material 3, and here we will discuss the cyclic acetal formation for carbohydrates. So if you have a diol or a 1,3 or a 1,2 diol, then it is a known reaction that they react with carbonyl compounds to form cyclic acetals. If you take 1,2 diol like ethylene glycol, then with a carbonyl compound like acetone, it forms a cyclic 5-membered acetal, which is known as the 1,3 dioxolane derivative. And if you take a 1,3 diol like propane 1,3 diol, then with a carbonyl compound like benzylidene, it forms a 1,3 dioxane derivative, which is a 6-membered ring acetal. And because carbohydrates, specifically monosaccharides, and their several derivatives, they can act as source of dihydroxy compounds, acetal formation with a carbonyl compound is thus expected for these compounds. There are two general rules that we have to remember. When the carbonyl partner, which is being reacted with the monosaccharide, is benzaldehyde, then it is a 6-membered cyclic acetal. That means a 1,3 dioxane derivative that is formed. And those derivatives are known as the benzylidene derivative. But when the carbonyl partner is acetone, not benzaldehyde, then the cyclic acetal is 5-membered, and such a derivative is known as the acetonide or isopropylidene derivative. So with benzaldehyde, 6-membered cyclic acetal, in that case the two hydroxy groups have to be 1,3 with respect to each other, and as for acetone, a 5-membered ring compound cyclic acetal forms. Therefore the two hydroxy compounds will have to be 1,2 with respect to each other. Why such selectivity, you might ask? In that case, let us illustrate this point by taking a simple polyhydroxy compound, a trihydroxy compound, a glycerol. Glycerol has 3 hydroxyl groups, and therefore it has the potential of acting as a 1,2 diol as well as a 1,3 diol. So you can imagine that when you are reacting glycerol with a carbonyl compound, then both 5-membered and 6-membered acetal compounds can be formed. When the reacting partner is formaldehyde, under acid catalysis condition, that is the condition for acetal formation, anhydrous condition, anhydrous acid catalyst being present, you do get both acetals, but one acetal tends to dominate the other depending upon the reaction condition. If you have kinetic control, which means lower reaction time, lower reaction temperature, then it is the 5-membered ring acetal which forms, where glycerol acts as a 1,2 dihydroxy compound. On the other hand, if you promote reversibility by elevating the temperature or carrying out the reaction for a much longer period of time, then it is the 6-membered ring acetal which is the dominant product, that is the B, which we have written here, and that's where the glycerol molecule is acting as a 1,3 diol. Now therefore we are forced to say that this one is the kinetically controlled product, KCP, and that one is the thermodynamically controlled product. Acetalization is a reversible process, therefore given you are promoting reversibility, B is forming at the expense of A, but A is forming faster. Therefore B is thermodynamically more stable than A, but A forms faster than B. That is the typical characters that are associated with the KCP and TCP. Now following this argument, with benzaldehyde, if it is reacted with a polyhydroxy compound, a 6-membered ring acetal compound will form, where the phenyl ring is placed preferentially at the equatorial position, assuming the approximate chair shape for the 6-membered cyclic acetal. Because as you can see, the hydrogen being placed as the equatorial, the axial position, the 1,3 diaxial interaction between these positions is minimum. But if you are to place this phenyl ring here and the hydrogen on that side, then it would have led to a much more steric hindrance. So 6-membered ring acetal formation with benzaldehyde is possible because phenyl can be placed at the sterically roomier equatorial position. What about acetone? Because we have seen that acetone, the acetonide derivative formation happens with 1,2-diol. 1,3-diol 6-membered acetal formation does not take place. That is because acetone has 2 methyl groups. The carbonyl carbon of acetone has 2 methyl groups. So one of those methyls must be placed at the sterically demanding axial position, which will lead to tremendous amount of steric crowding or van der Waals repulsion or 1,3-diaxial repulsion as we know it. Therefore, this is not a viable proposition. Therefore, benzaldehyde can form 6-membered ring acetals because phenyl can avoid steric hindrance. Methyls cannot avoid steric hindrance because there are a couple of methyls, and therefore you are forced to say that the 6-membered ring acetal formation will be kind of not good. What about the 5-membered ring acetal? Should we not get any sort of torsional strain or something like that? For the 5-membered ring acetal, you see the neighboring atoms are oxygen and they do not carry actually any substituents. They have just lone pairs. Therefore, the internal strain is less. 5-membered ring acetals are thermodynamically less stable as evidenced from this, but they avoid the undesirable van der Waals repulsion, and therefore in this case with acetone, the 5-membered ring acetals are actually more stable than the 6-membered ring acetal. What is the use of these reactions? These reactions are used to block specific hydroxyl groups or so-called protecting groups. These acetals are used as protecting groups to protect specific hydroxyls on monosaccharides or their derivatives, so that some of the hydroxyls are protected in the form of acetal, some of the hydroxyls are free. Those free hydroxyls are subjected to some sort of reaction, and then when you deblock, the acetals go away, you have a specifically functionalized carbohydrate. The question is which hydroxyls will react. That depends upon which sugar you are starting with. So let us start with that, the most common one, the glucose, and we will do these reactions with the D-glucose. But before going there, when you are reacting glucose with acetone, keep in mind that with acetone only a 5-membered ring acetal will form. Therefore, it is the 1,2 relationship, the hydroxyl groups that hold the 1,2 relationship, that means the vicinal hydroxyls, they will only react. And the second and another important point is that when the 2 hydroxyls are reacting with acetone molecule, the 2 hydroxyls of a ring are reacting with the acetone molecule and forming the 5-membered ring acetal. Those 2 hydroxyls must be cis with respect to each other, because if they are trans, then the 5-membered ring formation cannot take place, and that system is actually very unstable due to several types of strain. The 2 hydroxyls that are part of the ring and which are going to be the part of the new ring, they have to be cis with each other. Transfuse system will be true strand. So these 2 requirements we have to maintain. So if I draw the glucose in this way, in the cyclic alpha anomeric form, then the only pair of cis hydroxyls that I can spot from the Fischer projection formula is this pair, the anomeric OH and the C2OH. C2, C3 are trans, C3, C4 are trans, C4 and C5 is already part of a hemiacetal, so that is out of the question, and CH2OH, that is the C6OH, also is out of the question because there is no neighboring vicinal OH available. So 1,2 relationship has to be maintained. These 2 are 1,2, those 2 are 1,2, those 2 are 1,2, but the cis requirement is met only for this pair, and that is also evident from in the chair projection formula or in the Mills projection formula. As you can see, those 2 are cis, those 2 are trans, those 2 are trans, these are 1,3, therefore there is no question of acetal formation with acetone. So in the Fischer projection formula, we can draw the acetal formation in this way. In the chair formula, the acetal looks like that, and it looks very neat when you are doing this in the Mills projection formula. Obviously, anomeric OH C1 and C2 OH are now acetalized, but you have C3, C4 and C6 OH. Those hydroxyls are free, and you can subject them to several reactions, as we will see later. But in reality, when acetone is reacted with glucose under anhydrous acid catalyst, the acetal that we actually get is something different. It is not a monoacetonide but a bis-acetonide product. That means two acetone molecules react with one molecule of glucose. That is not possible in the pyranose form, but under acid catalyst condition, the hemiacetal can open up and then again close down, this time not using the C5OH but the C4OH, so that I have a furanose form. And in the alpha anomer of the furanose form, it is the C1OH and the C2OH which are still cis, and now because the C5 and C6, they are not part of the ring, because it is just a side chain now, it's not part of any ring, and therefore the cis requirement is not strictly required for these two hydroxyls. You can have acetonization here. That means one molecule of acetone can react with this pair, the other will react with that pair. This is the Mills projection formula of the furanose form, and this time when acetone is reacting, we are getting an acetonide here as well as we are getting an acetonide here. So because this is not part of the ring, there is no question of cis trans. But as these two hydroxyls are part of this ring, they have to be cis. Otherwise, their acetonide formation will fail. The Fischer projection formula of this diacetone glucose or diacetonide derivative looks like that. That is the Haworth projection formula, and this is the Mills projection formula. As you can see, C1 and C2OH, those are blocked. C4OH is obviously blocked. C5 and C6OH, that are also blocked, and it is actually the C3OH which is free. So whenever you react acetone with glucose, remember it is the diacetone glucose which is forming, not from the more common pyranose form but from the less common furanose form, where it is the C3OH which remains unreacted. One acetonide forms between C1 and C2OH, the other acetonide forms between C5 and C6OH. Okay, what about mannose? Mannose is the C2 epimer, no? So if you have C2 epimer, then you can have this acetone is somehow floating here. I don't know how that has happened. This should be coming here, but okay, let's not digress. So mannose means that you already have, if you take the alpha anomer, you already have the cis requirement met here, but these are not cis, those two are not cis, and these are 1,3, therefore they will not react with acetone. So again you should get a monoacetone mannose where the C2 and C3 OH groups have reacted. But just like in case of glucose, mannose also will react not in the pyranose form but in the furanose form, where this part is now not part of the ring, therefore the cis requirement is not needed, and it is this one, this C2 and this C3 OH which are cis to each other, and they will react. So you get a diacetone mannose which is just like the diacetone glucose, but this time it is not the C3 OH which is free, it is the C1 or the anomeric OH which is free. The C5, C6 OH are blocked, C4 OH is obviously part of the 5-membered ring, so it's blocked, and C2, C3 have formed their own acetal. Last time we were seeing acetalization between C1 and C2, this time we are seeing acetalization between C2 and C3. Okay, what about galactose? Galactose is the C4 epimer of glucose, and this time the molecule does not require to go to the relatively less stable furanose form. It can stay in the pyranose form and can form acetal or diacetone galactose between these two OH, which is the C1 and C2. these are cis, as you can see from the Fischer projection. C3, C4, those are also cis. C5 is part of the 5-membered ring. CH2OH, that is the C6OH, is 1,3 with respect to the C4OH, therefore with acetone it does not react. The Mills projection formula clearly demonstrates that you have cis relationship here and cis relationship here. So form these acetals and you will get the diacetone derivative or diacetone galactose, which is called the 1,2,3,4 di-O-isopropylidene D-galactopyranose. Typically a very long name that you associate with glucose. This is the 2,3,5,6 di-O-isopropylidene D-manofuranose. C1OH is free. Here C6OH is free. Rest of the things are already blocked. And here you have 1,2,5,6 di-O-isopropylidene D-glucofuranose, which is the glucose diacetone. Okay. Now if we react benzaldehyde, as we know that 6-membered ring is more stable than 5-membered ring, so benzaldehyde, because phenyl can be placed at a sterically roomier equatorial position, it has the luxury of I would say forming the 6-membered ring acetal, but 6-membered ring acetal formation that requires 1,3 hydroxyls. One hydroxyl, if one hydroxyl is 1, the other hydroxyl has to be at the 3 position with relative to the first hydroxyl, and the cis requirement is not valid anymore, because inside this box I have shown you that when you fuse two 6-membered rings, you can fuse them in a trans way or you can fuse them in a cis way. So if you have two hydroxyls which are 1,3 with respect to each other, they can form transfuse ring, they can form cis fuse ring. Therefore this requirement that you need a cis arrangement of the two 1,3 hydroxyls is not valid anymore. So what about we do the reaction on glucose? We have taken the glucopyranoside, which is the alpha ionomer here, and therefore let us check where do we get the 1,3 relationship and where can we form the 6-membered ring acetal. The chair form demonstrates that you have C4 and C6 placed in a 1,3 manner, and you can form a benzylidene derivative there where zinc chloride is being employed as the catalyst. So you have possibly acetalization here. This is the methyl 4,6-O oxygen benzylidene D-glucopyranose taken as alpha ionomer, and phenyl, as you can see, we have placed it in a equatorial fashion. It is difficult to see here, but if you draw the chair form, it is phenyl is placed here, and the ring junction is trans. One hydrogen is above the plane, that is the beta, and one hydrogen is below the plane, that is the alpha. But there is no problem because 6-membered rings can fuse in trans fashion, and the Mills projection formula demonstrates that you can draw the molecule in this way. So if you take the methyl glucopyranoside, you can selectively block the C6OH and the C4OH, whereas C2, C3OH, they remain unreacted. What about the C4 and the C2OH? Because you can see that the C2OH and the C4OH, there is a possibility that you can form a benzylidene derivative here. I keep repeating dibenzylidene. There is no dibenzylidene. This is only the diacetonide. So you can form a benzylidene here. So they are 1,3. They are cis. So they look very promising. But if you inspect this figure, then it is almost impossible to form any sort of linkages between those two. That ring will have to be really very large, and you cannot possibly bridge these two by using the single carbonyl carbon of a benzaldehyde. Unlike that, you can form these two here. So benzylidene acetal formation involving the C2 C4 is not possible, but because C6 is attached to the ring with a single bond and it can rotate freely, so here you cannot form the ring, but in this direction you can obviously form the ring. What about galactose? Take the galactopyranose alpha ionomer methyl glycoside of galactose. So in this case you have C4 and C6OH again placed in such a way that it can form a benzylidene derivative, and this time if you inspect, these two hydrogens are both projecting downward. So this one is a alpha hydrogen, that one is also alpha hydrogen, alpha meaning projecting downward in the chair form, and therefore this ring junction is cis. And this time you have the C2OH and the C3OH. Again you have C2 C3OH, they are available to you, but because galactose is a C4 epimer of glucose, this one is the C4 epimer of glucose, here you have trans junction, here you have cis ring junction, but the OH groups, their identity are the same, that is the C2 and the CC33OH, which are free. Let's see how we can use these things to carry out certain conversions, and these are important for your university exams. So suppose they have asked you to convert D-glucose into 2,3-diomethyl D-glucose. So you need to functionalize this OH and that OH, but protecting that OH, that OH and that OH. So you need to protect these two OHs, need to be protected. That means you should go for a benzylidene protection, because those two are like the ideal candidate for 6-membered acetal formation, and they are 1,3 with respect to each other. What about protection of the anomeric OH? Anomeric OH can be protected very easily in the form of glycoside. So you do a Fischer glycosidation first, so that makes it OMe, and then you do the reaction with benzaldehyde in presence of zinc chloride, so that makes it the cyclic acetal, the C4C6OH, they are protected in the form of benzylidene. Then you have the methyl iodide reacting with sodium hydride, and the in presence of sodium hydride, it is the two hydroxyls which are deprotonated and they react with each other, forming the corresponding O-methylated derivatives. And of course you can now subject this to dilute acid hydrolysis, so that the acetals are deblocked, and this one is being acetal is gone. Those two will remain, because remember, these are the ether linkages, these are not the acetals, so they will not be cleaved, they will remain, and you will have your target molecule. Next, they have asked you to functionalize only this part, this part. Well, that requires protection of these two, which is obviously is a 1,3 relationship, and protection of that too. If I am to protect these two, then I can go for acetone protection, but in that case it is not this OH will become protected, but this which will become protected in the form of the 5-membered ring. It is this oxygen which will come out as OH, and those two will be protected, because this time when you subject it to acetone and dry acid, it is the furanose form which reacts and diacetone glucose forms. So functionalization specifically at C3 will call for protection with acetone, where anomeric OH, C1OH and C2OH are protected, C5OH and C6OH are protected, C4OH is part of the furanose ring and is therefore protected, C3OH is free, you methylate it under reaction condition, and then you hydrolyze and you get your corresponding furanose derivative. So this time you have OH, OH, and this is OH and OH. Now everything is free, so this is a hemiacetal, this will open up and then again close down the ring, but this time it will close down the ring using the C5OH, and you will get the familiar 6-membered ring, but only the C3 oxygen is methylated. They have asked you to convert D-glucose to DLO, so you need to, that's a C2 epimer, so this one has to be, the configuration has to be inverted. I'm sorry, this configuration has to be inverted, because it is the C3 epimer of glucose. Allos means everything, C2, C3, C4, C5, everything is on the same side, because you have started from D, everything will be on the right side. For glucose, it is the C3OH which is on the left side if you take the D-glucose, so C3 epimerization is required. So need to protect again, you need to protect these two, you need to protect those two. Again, it is a functionalization for the C3. So I will go for the diacetone protection. Do the diacetone protection and then do a reduction, an oxidation, so that the secondary alcohol is oxidized to the corresponding carbonyl group. When you deploy sodium borohydride, because this is a chiral center, that is the chiral center, here we observe using a chiral reducing agent but a chiral substrate, we observe a diastereoselective reduction, and the major product is the OH is on the alpha side. That means it is below the plane of the ring. These two are like trans with each other. The detailed explanation for this diastereoselectivity is beyond the scope of this discussion, but remember, this is not entirely unexpected because our substrate is chiral. Either this one or its diastereomer where the OH is projecting upward, either one of them could have been the major product. It is fortunate that our desired outcome has been achieved here. Deblocking will generate OH, 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 OH. That's a hemiacetal. Ring will open up, again closes to form the familiar 6-membered ring where the C3OH has been from alpha, it has now, from beta, it has now become alpha. So we get a D-allose. So C3 epimerization is achieved. Next, they have asked you to do a deoxygenation at the C3. Again, repeatedly they are targeting the C3. So if they are targeting the C3 only, you always go for diacetone protection. So you need to knock this thing out and drop a hydrogen here. So this can be done in sophisticated ways, or you can go for a kind of a more crude way. So first do the diacetone protection. This is C3OH is free. Go for a xanthate formation. Okay, go for a xanthate formation so that you have a xanthate here, because this is something which you have encountered in your elimination reactions discussions in Shugaev elimination. But this time we are not going to do any Shugaev elimination. We are subjecting it to a treatment with tributyl tenhydride and the radical initiators such as azoisobutyryl nitrile AIBN, and this thing will completely remove this group and install a hydrogen here so that a deoxygenation is accomplished. That's a Barton-McCombie deoxygenation and goes obviously via a free radical pathway. As you can understand that a free radical generator is supplied here and the mechanism is outlined here, but this is not in your syllabus. If you want to do this thing in more, in a less sophisticated way, let's put it that way, then just convert this OH into tosylate by treating this thing with tosyl chloride pyridine. Everything else is protected, only this OH is available, so this will become OTS. And then treat that sulfonate derivative, the tosylate derivative, with lithium aluminum hydride. So there will be a kind of a nucleophilic substitution here, SN2 reaction, and you don't really care because you are going to end up with a couple of hydrogens here, so this thing will eventually not be a stereocenter. So you do the displacement, nucleophilic displacement. So that's a reduction as well. So hydrogen hydride comes and OTS leaves, and you are left with this one, and treat this with HCl H2O so that your acetals are deblocked and you get your 3-deoxy-D-glucose. So this is a rather fancy way of doing it, and I have incorporated this because maybe you will have utility of this thing in some interviews or something like that. But if you are not bothered about this thing, then it's no big deal. You can always convert this OH to hydrogen by some more conventional way. And now let us convert D-glucose to D-xylose. Now this one will require knocking off one of the carbons. And which carbon? The xylose is this, that's a aldo pentose, and glucose is an aldo hexose. And comparing the configurations, we can see that if we can somehow manage to knock this CH2OH out, then it would be great. So first do the acetonide protection, diacetone glucose formation via the furanose ring, and these two acetals, one of these acetals is comprised of two secondary hydroxyls, while other has one secondary hydroxyls, the other is a primary hydroxyls. That acetal is a little bit more susceptible to acetal hydrolysis compared to this one. So if you can carefully select the reaction condition where a selective deacetalization can take place, then you can free the C5 and C6OH while keeping the C1 and C2OH still engaged in the blocked form. And you do that with acetic acid and water, mild condition, selective deacetalization has taken place. Now you have the C3OH, the C5OH and the C6OH in the free form. Now C3OH is not a vicinal diol, because this OH is protected, that OH is protected, but this is the only vicinal diol that you have. If you subject it to a oxidative cleavage via sodium periodate, just like a Lemieux-Johnson oxidation, then this thing will be cleaved and you will get a aldehyde here. The C6OH is successfully knocked off. Now all that remains is to reduce this C5 carbonyl to the corresponding primary alcohol. You can do that with hydrogen nickel, and then treat this thing with dilute acid, so that the xylofuranose results, which opens up and then closes down the ring. But when it closes down the ring, it uses not the C4OH but the C5OH to close down in a pyranose form. So you have your target molecule. Finally, the conversion is from D-glucose to methyl 2,3,4 tri-O-benzyl. So you have CH2PH groups installed here, D-glucose. So need to functionalize C2, C3 as well as C4. Need to protect this one, and this one can be easily protected. Need to protect this one and need to protect that one. So that protection is very easily done by Fischer glycosylation. But how to protect these primary hydroxyls at the expense of these secondary hydroxyls? Well, obviously you know that trityl chloride can do the job, because due to steric hindrance it is only the primary hydroxyl which is protected, and these three are not protected. So you protect it, and then you subject it to a deprotonation by sodium hydride. So these are alkoxides are generated, and you do a benzylation with benzyl bromide, which is a very powerful electrophile, and you are promoting the reaction in DMF medium, which promotes the SN2 by molecular nucleophilic substitution. So benzylation has taken place at C2, C3 and C4, and C6OH is protected in the form of trityl, and this one is OMe. And we also know that trityl ethers can be cleaved where the acetal linkage is not disturbed by treatment with acetic acid water, just like you have used acetic acid water here. This trityl will go, and this will become OH, and this will remain the OMe, and therefore you have done your job. You have converted D-glucose to methyl 2,3,4 tri-O-benzyl D-glucose. Okay, this much for the cyclic acetal formations. What about osazones? Well, that will require reactions of sugars with phenyl hydrazine, and this thing we will discuss now. This is a very important reaction as far as configurations of sugars were concerned. Emil Fischer's ground breaking and epoch making work was critically dependent upon this reaction. Way back in 1875, Fischer accidentally sort of prepared phenyl hydrazine when he subjected the benzene diazonium chloride under the reducing environment with sulfur dioxide in aqueous medium, what he got was phenylhydrazine. And this phenylhydrazine many years later served him well in his quest for the determination of the relative configuration of sugars. Sugars are generally extremely difficult to crystallize, and the time at which Fischer was working, it was also very important for him to obtain crystals, because characterization of compounds could be done by melting point determination, and accurate melting points can only be determined if you have a crystal in your hand. Sugars proved to be notoriously difficult to work with. However, Fischer observed that if carbohydrates, monosaccharides, are subjected to treatment with excess phenylhydrazine, then they form beautiful crystals. And not only that, there is a tremendous observation that glucose, fructose and mannose, those three were known to be different compounds. When treated with excess phenylhydrazine, all of them formed the same crystalline derivative. These crystalline derivatives were known as osazones, and that was a critical point in determining the relative configuration of these hexoses. Now, so this is what we are talking about. So you have D-glucose, you treat it with one equivalent of phenylhydrazine, you get the corresponding phenylhydrazone. Then you subject it to yet more two equivalents of hydrazine, phenylhydrazine, then you get corresponding osazone. The same osazone can be accessed from D-mannose. When D-mannose is treated with one equivalent of phenylhydrazine, you get the corresponding phenylhydrazone, which again when treated with excess phenylhydrazine, rather two equivalents, you get the same osazone. Strikingly, fructose also gives rise to the same osazone when it is treated with the excess phenylhydrazine. In all these cases, when you treat this thing with excess phenylhydrazine, one molecule of aniline is eliminated and ammonia is eliminated, and obviously in this case a water molecule will eliminate, and in this case one water molecule will also eliminate. So what is happening? So the first part is kind of okay, the first part, because that's a nucleophilic addition elimination pathway, elimination of water, formation of the corresponding tetrahedral intermediate, and then elimination of water will give rise to the corresponding phenylhydrazone. And if you look carefully, the osazone is actually the oxidation product, because this time when you are converting D-glucose to the corresponding phenylhydrazone, the oxidation state of this carbon is not changing. But when you are getting the osazone from the corresponding phenylhydrazone, the oxidation number of the C2 is changing. Same is here. And it is the oxidation number of the C1 that is increasing when you are starting from the D-fructose. So basically, the C2 hydroxyl groups of the phenylhydrazones of the D-glucose and D-mannose, those have been oxidized. In addition, the C1 hydroxyl of the fructose is also oxidized. How is this happening? And somebody is getting obviously reduced, so we are getting ammonia and aniline. This is obviously a reduction of phenylhydrazine, because if you look at phenylhydrazine, you are removing this NN bond, you are adding one hydrogen here and one hydrogen here, so obviously these two nitrogens are getting reduced. So the mechanism was very tricky to find out, and people were pondering over it for a very long period of time. Fischer himself could not come up with a reasonable explanation, and his work did not hinged upon the mechanism, but what he proposed was found out to be untrue, at least in the mechanistic aspect. And here we outline which is believed to be the correct mechanism. So you do the reaction with an aldose. You can do the reaction with ketos as well, but let's do this reaction with an aldose. So the first thing is usual reaction of carbonyl group, formation of the phenyl hydrazone. Then an imine-enamine tautomerism takes place, where this alpha hydrogen migrates from this carbon to that nitrogen. This is like a allylic shift. Once that has happened, this is also akin to the Amadori rearrangement. Amadori rearrangement is conversion of alpha hydroxyl imine into alpha ketoamine. So you have a alpha hydroxy aldehyde which is reacting with primary amine to give you the alpha hydroxy imine. If you look carefully, this hydrogen can migrate and put a double bond here, go over to this nitrogen. Okay, but if you have a double bond here, then that's not an ordinary double bond. It's a enamine as well as it's an enol, because carbon oxygen double bond is stronger than carbon nitrogen double bond. It will tautomerize in this way and it will generate a carbonyl here. So that's a alpha ketoamine that you get. That's the Amadori rearrangement, and this shift is very similar to that. Therefore, it is the imine-enamine tautomerism, just like the Amadori rearrangement. Within this molecule, there is a shift of this proton, and this nitrogen bond will now break, because this is a weak bond. Carbon oxygen double bond is a strong bond, so it will form, and we will also get a carbon nitrogen double bond here. So you have a imine linkage, you also have a carbonyl linkage, and one aniline molecule is gone. You also have now excess phenyl hydrazine. So those excess phenyl hydrazines will now react with this imine to give you a hydrogen linkage here. From this carbon you will lose an ammonia molecule, and from that carbon again reaction with one molecule of phenyl hydrazine will give you another phenyl hydrazone derivative with the elimination of water. That is the osazone. So if you look, it is the C1 and the C2 which are reacting, and it does not matter in which direction the Ca hydrogen is or the OH is. So any aldohexose which has the same configuration at the C3, C4, C5, but the different configuration at C2, that is C2 epimeric aldohexoses, or any aldopentoses which are C2 epimeric with each other, they will react in the similar fashion and they will give the same osazone, because from this carbon onward nothing happens. So their configuration remains the same. So glucose and mannose, they will give the same thing. And if you note that the fructose, which is the ketohexose, also has the same configuration at the C3, C4, C5 corresponding to D-glucose as well as D-mannose, D-glucose and D-mannose. That is which we have highlighted. You are tasked with this, coming up with a mechanism for the ketohexose. Say take for example a CH2OH and a C double bonded O here, do the same sequence of reaction and see whether you can come up with the phenyl osazone. Now, what is the proof that this mechanism is operating? Isotopic leveling is obviously a proof. It can serve as a proof, just like we have seen in Fischer-Indole synthesis. So you do the reaction with a labeled nitrogen, where the remote nitrogen of the phenyl hydrogen is labeled. So the first step is, okay, we know that this nitrogen will attack here, and that nitrogen is less nucleophilic because of the conjugation with phenyl, etc., etc. Those are trivial things, you know that. So that nitrogen is labeled, and if our mechanism is true, then this nitrogen will eventually be eliminated as ammonia, and that nitrogen will be eliminated as aniline. So do the reaction, check the aniline is not labeled, but the ammonia that is coming out, that is obviously labeled. So this is a clue that this reaction is proceeding via the mechanism that we have outlined here, this Amadori rearrangement that we have seen here. The next big question is, Why does not the reaction proceed beyond C2? Because if you have a carbon nitrogen double bond here and that hydrogen can shift here, then you also have a carbon hydrogen bond here. Obviously you have, and you also have a C and double bond here, so that hydrogen could have migrated there and the same cycle would have been repeated, and I would have got a C double bonded O here, and that would have reacted with yet another equivalent of phenyl hydrazine. So that's not happening. Why? That is because it is believed that after the introduction of the phenyl hydrazine onto the C2 and C1, they form a stable hydrogen bonding complex where either this nitrogen acts as a hydrogen bond donor while this one acts as an acceptor, or that nitrogen acts as a hydrogen bond donor and this nitrogen acts as an acceptor, and this stabilizes the molecule and prevents it from further reacting. So this question is also being asked. They also ask this question. So I would say that it would be a good idea to remember why the reaction does not proceed beyond C2 or stops at the C2 stage. So that's it. That's for the osazone and the cyclic acetal formation. I hope that you have found this lecture at least a little bit useful. I thank you for your patience and I will be seeing you in the next one.